Nitrocellulose is a highly energetic compound with a fascinating history and some very unique properties. Compared to a lot of the energetics I've made in the past, nitrocellulose is super simple to make. It's also a whole lot safer and frankly more entertaining to demonstrate. When ignited, nitrocellulose burns away nearly instantly in an impressive fireball. This reaction is so predictable that performers have long ignited the stuff by hand as part of the act, although I don't recommend trying this yourself. On top of all that, nitrocellulose was the very first synthetic plastic, which I'll get into a whole lot more later in the video. Now, before anyone gets upset in the comments that I would imply any energetic is safe, I want to clarify that this procedure is still very dangerous, and that trying to make some yourself without any background chemistry training whatsoever would still be a very bad idea and potentially result in significant injury. This procedure has also been done in some way or another dozens of times already here on YouTube, so the information is already widely available. With that said, my qualifier is that nitrocellulose doesn't produce or require nearly as many extremely toxic chemicals as the other energetics I've made on this channel do. It also won't detonate if the reaction runs away, or really at all except under very deliberate conditions. With all that, let's go ahead and make some. Now, the first method I used to make nitrocellulose began by making a simple nitrating mixture. This is simply done by carefully adding 35 milliliters of cold fuming nitric acid to 50 milliliters of cold 98% sulfuric acid. The fuming nitric acid can be substituted by simply using 50 milliliters of 67% nitric acid, but I've had trouble fully nitrating cellulose with anything lower than 90%. This mixture was then carefully mixed before slowly adding 3.5 grams of cotton balls to the mixture. I usually use cotton balls because they're a reasonably pure source of cellulose, but technically any source of cellulose would work just fine. This mixture is then allowed to sit for about 20 minutes and then very slowly heated until the structure of the cotton balls falls apart and the mixture becomes a heterogeneous slurry. For me, this happened around 60 degrees Celsius, but it could happen sooner or even later. The slurry was then poured into a liter of distilled water, aggressively stirred, and then passed through a coffee filter to collect my nitrocellulose. As soon as the filtering step was complete, the still very acidic nitrocellulose was rinsed in another beaker of 10% sodium bicarbonate. This is done to remove any residual acid and to prevent the formation of the spontaneously combustible compound pyrocellulose. After about 5 minutes, this was filtered a second time and then rinsed thoroughly with a good deal of cold water. The now completed, but still very wet nitrocellulose was then placed on a watch glass and allowed to dry overnight. Now, the cool thing about this first method is that it results in the formation of nitrocellulose with a nitrogen content in excess of 13%. This is referred to as insoluble nitrocellulose or guncotton, and its extensive use during the American Civil War is one of the primary reasons that this conflict is seen as the first modern war. When used as a propellant, guncotton creates roughly 6 times as much gas as an equal volume of gunpowder, while only creating a fraction as much smoke and heat. This made conventional weaponry dramatically more effective, and by filling hollow cannonballs with the stuff, nitrocellulose also represented the first usage of explosive artillery shells in warfare that I'm aware of. Anyway, to demonstrate my first batch of nitrocellulose, I simply poured a little onto a watch glass and then ignited it with a butane lighter. This created an immediate and impressive tower of flame that lasted a bit longer than the nitrocellulose made using my second method. As you also might notice here, the nitrocellulose left behind a definite film of crap on the watch glass. Ideally, nitrocellulose burns clean, leaving nothing behind, and this could be due to a poor final job rinsing my final product, or incomplete combustion. Now, before I move on to my second method, I want to point out that nitrocellulose isn't actually a nitro compound, but actually a nitrate ester, and should probably be called cellulose nitrate. If the esterification is conducted at higher temperatures, the primary product will be trinitrocellulose, which was the case here in my first method. As I pointed out earlier, the nitrocellulose I made contained an excess of 13% total nitrogen. However, by conducting the reaction at lower temperatures, you can favor the formation of dinitrocelluloses over trinitrocelluloses. This creates nitrocellulose with a total nitrogen content lower than 13%, which has some very unique properties of its own. Also, I feel like since I used the word weaponry a minute ago, I need to clarify for YouTube that nitrocellulose cannot, under any circumstances, be used in this form in any weapon ever under any circumstance. Weapons-grade nitrocellulose requires extensively more processing after this point, which I'm not gonna show in this video, and therefore am not showing how to make any weapon or anything resembling a weapon. Just to be very, 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 very clear on the matter. This is for science. Regardless, I am happy with how this first run went, so I'll show you my second method, which is frankly a lot easier. For my second method making nitrocellulose, I began by simply adding 50 milliliters of 98% sulfuric acid to a beaker followed by 25 grams of potassium nitrate. I then stirred the mixture until the potassium nitrate was completely dissolved, which resulted in a simple nitrating mixture. The advantage of making the nitrating mixture this way is that it doesn't require any nitric acid, and instead uses much more accessible nitrate salts. The disadvantage is that this really can't be easily used in other low-temperature nitrations, as the potassium nitrate, or rather potassium bisulfate, has the tendency to crystallize out of the mixture. It can also be a bit finicky about side reactions in my own personal experience. In any case, once the two were thoroughly mixed, I cooled the mixture down to room temperature before again adding 3.5 grams of cotton balls. This time I simply allowed the mixture to sit and react with no applied heat for an hour and then dumped out as much of the nitrating mixture as I could. The nitrocellulose was then rinsed thoroughly with cold water, which is then dumped off before a second thorough rinse with 10% sodium bicarbonate to again eliminate any remaining acid held within the fibers. At this point, the nitrocellulose can be safely handled, with gloved hands. And so for the final rinse, I actually just took it over to the sink, as the more defined structure of this second batch allows it to be safely rinsed under running water. Once I felt the nitrocellulose balls were as clean as they were going to get, I squeezed as much remaining water out of them as I could before allowing them to dry overnight. When I came back the next day, I was greeted by my clean and dry nitrocellulose ready to be burned. Superficially, this stuff looks nearly identical to the initial cotton balls, except maybe with a slight yellow hue that's kinda tough to see on camera. At this point, I went ahead and weighed both of my batches, giving me a final mass of 4.26 grams for my second method and 4.19 grams for my first. I'm not sure if this is good or what a percent yield would even look like, as these are both complex mixtures of mono, di, and trinitrocelluloses, all with different molecular weights. I do think the recovery from the first batch was a bit lower due to losses trying to collect a loose powder, because that one should definitely be higher, not lower. Also, if you're confused as to why my first batch still exists, I made both batches before burning anything, and my presentation is a bit out of order. Anyway, when ignited, the nitrocellulose made the second way goes up in a burst of flame that lasts only a fraction of a second, and leaves behind basically no residue. The reaction actually happened so fast that I eventually switched to using my phone camera, as it can record at significantly higher frame rates than my DSLR. Filming it this way really shows how quickly energy travels through the nitrocellulose as it ignites, which I found pretty cool to see. Now, the interesting thing about this second method is that it favors the formation of dinitrocellulose, and so tends to produce nitrocellulose with a nitrogen content lower than 12%. This is referred to as soluble nitrocellulose, or colloidon. As I mentioned earlier, the degree of nitration of the nitrocellulose product in both methods is a function of the reaction temperature, and so the first method could have been conducted without any applied heat to get the same result. The second method could also theoretically be done with applied heat to produce the trinitrocellulose as well, but in my own personal experience, this has usually resulted in a blackening of the cellulose by sulfuric acid. Regardless, soluble nitrocellulose, as the name implies, is soluble in certain organic solvents, and classically in a mixture of ethanol and diethyl ether. This dissolved nitrocellulose is a viscous lacquer that leaves behind a colorless, transparent, and flexible film when it dries. This made nitrocellulose lacquer the standard for automobile, furniture, and instrument finishes for decades. Newer alternatives for automobile coatings have obviously superseded nitrocellulose since then, but due to the classic-looking yellowing effect that nitrocellulose has on wood, it's still widely used in furniture manufacture, as well as every guitar produced by Gibson. It's also still used in most nail polishes to this day. Apart from its use as a lacquer, nitrocellulose was actually the very first plastic ever developed. This first ever plastic was called Parkesine and was patented in 1862 by Alexander Parkes. In 1868, American inventor John Hyatt improved on Parkes' invention by plasticizing the nitrocellulose with camphor so that it could be processed into a photographic film. This second ever plastic he called celluloid, and it became the industry standard for photographic film. This is why most of the oldest films were lost to time, and why old film has a reputation for being extremely flammable. In fact, this specific use of nitrocellulose is the cause of what is by any metric the deadliest era of Hollywood. You have to remember, films that were shot on nitrocellulose were rapidly dragged across hot carbon rods during screening, and if it was to ignite, which it often did, it couldn't be put out. Nitrocellulose contains enough oxygen in its nitro groups that it doesn't need any from the air, so once it's ignited, it's gonna keep burning until it's total combustion. Even attempting to douse the burning nitrocellulose in water would only produce copious volumes of lethal nitrogen dioxide gas. This is actually why projection rooms exist, even to this day. It would be a lot easier and cheaper to put the projector in the center of the theater, but instead they started building separate rooms to house the extremely flammable reels. These rooms were designed with automated fire shutters that would slam down in the event that the reel caught fire, often trapping the projectionist inside a fiery tomb. This gruesome fate was far from uncommon, with a 1936 publication claiming one American projectionist died every 18 days in this manner. Eventually, nitrocellulose film was replaced by cellulose acetate, which was marketed as safety film. These days, cellulose acetate really only sees use in the filming process, while most intermediate splicing steps are done using polyester. Another final use of nitrocellulose plastic was in the textile industry, and was the basis for the first synthetic silk called rayon. However, nitrocellulose rayon was much more flammable than cupro-ammonium rayon or cellulose acetate rayon, and was again quickly discontinued. Anyway, the idea of extremely flammable plastic seemed really cool to me, so I decided to give it a try, which turned into several tries. For my first attempt, I started by simply making up another batch of nitrocellulose, allowing it to dry, and then putting it into a beaker. I then added some acetone and stirred it up a bit, which quickly began to dissolve the nitrocellulose. Eventually, after a good while of vigorous stirring and a lot more acetone, I realized that some of this nitrocellulose was simply not going to dissolve. This could have been due to overnitration, but was more likely an undernitration of the inner parts of the cotton balls. Regardless, I decided to go ahead and remove as much of the insoluble nitrocellulose as I could by passing the mixture through a strainer. I then transferred the gooey, partly dissolved nitrocellulose into a petri dish to dry. The somewhat filtered nitrocellulose lacquer was then poured into a second petri dish in hopes that I'd be left with a somewhat clear circular piece of plastic once the acetone evaporated. I also tried pulling some of the nitrocellulose into a syringe and squirting it into a beaker of water to try and precipitate something resembling crude rayon fibers. This didn't work terribly well, so I scrapped the attempt pretty quickly. When I came back to my petri dishes of nitrocellulose lacquer the next day, I found that the majority of it had dried into a brittle white puck that contained a lot of the insoluble fibers. However, all around the sides of the dish there was a thin film of clear nitrocellulose plastic, which I was very excited to see. This confirmed that I had indeed made some soluble nitrocellulose. The problem, though, was that a decent amount had remained insoluble, and the only reason the nitrocellulose around the edges cleared up like this is because the insoluble fibers had settled out to the bottom. I did really want a solid piece of clear nitrocellulose plastic though, so with this in mind, I figured I'd give it another shot. For this next attempt, I decided to use ash-free filter papers as my source of cellulose. These are a lot more pure and uniform cellulose than cotton balls, and I figured they would nitrate much more cleanly. I also used a stoichiometric quantity of fuming nitric acid this time and never allowed the reaction mixture to exceed 25 degrees Celsius during the 30-minute reaction. This final batch was neutralized, washed, and dried just like the earlier runs, and then transferred to a beaker along with some acetone. Sadly, this also resulted in a whole lot of insoluble material, which in a last Hail Mary effort I tried to remove using my centrifuge. The supernatant was then poured off into a petri dish and allowed to dry. This is how it turned out the next day, and as you can see, it still wasn't anything resembling a clear plastic. Now at this point, I was starting to get annoyed that I wasn't getting a clear plastic, and so I decided to do one final, very careful attempt. For this final run, I basically repeated my previous procedure using the filter papers. I then followed this with a second nitration of the cleaned and dried nitrocellulose at 40 degrees Celsius for an hour. This resulted in the nitrocellulose beginning to fall apart the way it did with my first attempt, but not nearly to the same extent. Since the particles of nitrocellulose formed in this run seemed a bit bigger and more durable than previous runs, I decided to try cleaning them using my vacuum filter this time, which actually worked pretty well. After allowing this final batch to dry overnight, I transferred it all to a beaker and again tried to dissolve it in some acetone along with 1 gram of camphor this time. I opted again to centrifuge out the small undissolved particles, even though so far it seemed this batch did dissolve much more cleanly than the earlier attempts. After running the tubes for 5 minutes at 4,000 RPM, I poured 2 of them out into another petri dish and set it aside to dry. In the meantime, I decided to try painting the stuff onto a piece of wood with a cotton ball to see if it could make a decent lacquer. After allowing it to dry on the wood for 15 minutes, you can see that the nitrocellulose had formed a nice, clear, and fairly water-resistant finish. I next decided to make another attempt at some rayon fibers by injecting this stuff into some cold water. It still didn't work well, but at least this time the extruded nitrocellulose stayed together as mostly single pieces. I feel my technique is more the problem here, and so feel free to comment if you have a better idea how this could be done. I also tried dripping the nitrocellulose lacquer onto the surface of the water, which spread out into these thin films that dried white. I'm not sure this could be useful in any way, but it was still pretty cool to see. Anyway, at this point, the nitrocellulose in the petri dish had finished drying, and I was thrilled to see that this time it was all very clear. Adding the camphor did seem to make the puck a lot tougher, which made it a lot harder to get out of the dish, but a whole lot more flexible once it was out. This piece did have a lot of wrinkles in it, as I think I got a little impatient with my drying process, so I decided to dissolve it back down and pour it into a new petri dish to see if I could finally get a clear piece of plastic. This is my final product, and while it still isn't perfect, I think it's as close as I'm gonna get. It certainly isn't completely smooth, but it is entirely transparent and highly flexible. I also poured a little out into another dish to try to make the thinnest film I could, which gave me this nice little circle of cellophane film. This stuff is even clearer if you ignore whatever's going on in the center, and it has that nice classical sound of cellophane when you crinkle it. This was really cool and all, but like I talked about earlier, this is the exact stuff that was so incredibly flammable that we had to design containment death boxes to show films on it. With that, I decided to burn my pieces of plastic, and boy did they ever burn. I don't know what it was about this last batch, but I'm gonna stop talking for a minute so you can hear how intensely it burns once it's been ignited. Anyway, I hope you enjoyed this video, and I'm sorry it's taken so long to put a new one out. Holidays are always particularly busy for me as it is, but I've also spent a lot of time lately expanding onto projects I had already considered finished, like this one. As a quick update on my Patreon, I've now submitted 3 different appeals over 3 months and received no word back. Eventually, I reached out to Patreon on Twitter, and after both tweeting and DMing both Patreon and their support account, I did eventually receive a response that my appeal is still pending, and so I'll update if that ever goes anywhere. On that note, I do want to thank everyone who has contributed to the work I do on this channel, whether you've been a patron, a member here on YouTube, or even someone in the comments offering valuable advice. It does all mean a lot to me, and I hope you all continue to support me in this project. If you liked the video and you want to see more like it, consider subscribing here on YouTube or checking out my TikTok while it still exists. Thank you all so much for watching, and I'll see you next time.